And what's controlling the hazard at Diablo Canyon, and what's controlling the uncertainty? So there were different answers, right? What controls it? So Nick was showing that what he's seeing that controlling the short period ground motions were the standard deviations, right? The sigma model is controlling. And if he's looking at the medians, the strike slip median is more important than the reverse median on the hazard. That's a little bit opposite of what you might expect if you're thinking our hanging walls are really uncertain and is that driving it? So it's not the difference in the at least combined effect of hanging wall and the reverse models is not as important as the basic difference in the strike slip models. Okay, so we've got to keep track of what matters. At 1 hertz, long periods, it was the GMPE medians that were driving the difference between the answers, not the sigma models. Okay, so this is partly to help us focus our discussion going forward. What do we need to pay attention to? Where do we use numerical simulations to help us? And where do we just rely on the empirical data? Okay, though Melanie made a good point, agreement in the models doesn't mean no uncertainty. Okay, it can all just mean we agree on the best estimate, but we all have a wide range of uncertainty. And so we've got to get back and be sure that we have the uncertainties captured in there. That's partly what was in our current epistemic uncertainties. All right, so you didn't pass the Diablo Canyon test, all right? So what controlled at Palo Verde? At short periods. So let's start at long periods, the easy one. What's controlling at Palo Verde at long periods? Large distant faults, right? And what's controlling the uncertainty? One was a whole lot bigger than everything else, the median, right? Okay, so the median is really important for large distances. We can get at that, though, empirically, when we start to look at the data that we've got from the distant Arizona events, and we can try to calibrate our models instead of just extrapolating them to larger distances, right? Because we have a real problem with some of the older models in particular working out beyond 100 kilometers and staying way too high. My model does that. Okay, it's off by factors of 2 out there. Okay, what about at short periods? The distance showed up still at 10 to the minus 4. 10 to the minus 6, it's all the local normal, which means the normal faulting factors, right? Which we may not know nearly as well as what the agreement showed there. Okay, so part of what we want the modelers to talk about tomorrow as we're starting to go forward is how well do they really know normal faulting factors? We may all be putting a number near 0 or 10%. Is it really constrained in that range, or how big can it, how far off can it be? Okay, and then the sigma model started to show up there, right, at that period. Okay, so we put you through that torture for a reason, right, in terms of seeing all those plots, so that we can try to focus what we're going to be talking about. So any broad questions about what's controlling and what's important here?
This is Tom Heaton, Caltech, and I'm curious, for like Palo Verde, a normal faulting environment, we're mainly working on ground motion prediction equation uncertainties. I mean, the other issue out there is, could there be a strike slip earthquake hiding in there? And so when we go to normal faulting areas, it's very common to see normal faults coexisting with strike slip faults. And given that you see a obvious lineation practically running through the site, why isn't there a logic tree branch that says, could there be a strike slip fault through here? Or is that excluded from this analysis?
So there are 2 parts. There's source characterization and there's the ground motion model. So our charge here is the ground motion part. Okay, the source characterization people for Palo Verde are dealing with relative, how much is normal events, what is the relative rates of strike slip events. Do you know what that answer is? Because they're both there. It's not all normal.
Hi, this is Melanie Walling, hazard analyst for Palo Verde. So there is a strike slip fault, the closest one, which is the sand tank fault. And you know, so strike slip faults were considered, and it's around 60 kilometers from the site. But it's the Sonoran Basin and Range is an extension region, and so it's completely normal. And the faults that have been mapped out as strike slip, or have the faults near the site, have all been identified. And the ones that have been strike slip have been run in hazard as a strike slip.
But Melanie, in the background zone though, are there strike slip as well, or is the background all normal events?
There is a background that has 40% strike slip, so
Okay. So there's a mixture there, Tom. It's 60% normal, 40% strike slip in the background. Is that correct?
It's for about two of the background sources.
Okay. So some of it's in there, but fundamentally that's not our charge. Our charge is to make models that work for both cases here. Any other questions? Better that you ask rather than I give you another quiz, right? Tom, see, I can always rely on Tom to speak up.
Okay, I'm not eating here. In the logic tree analysis.
I can't hear you, Tom, on the mic.
It's on. Check, 1, 2, check. Not coming up. So in the logic tree analysis, I'm not an expert in logic tree, but usually in mathematics, when you say a logical analysis and conclusion, you say, I've got A, B, C, D, and if not A, then B, or A plus B, and things like that. But generally, when you go through a logical analysis, all possibilities add up so that it's a closed set. But when this goes through a logic tree, shouldn't there be a logical branch that says, what's the probability it's none of the branches considered? I don't understand how it can be a true logical analysis unless it closes.
No, so you're correct, and so you would think, what would the weights represent, and are they representing probabilities, and are these alternatives, you know, mutually exclusive and collectively exhaustive? And the answer is no, at least I will say. So I'll give you my own opinion on that problem. What we're giving our weights on models, and now we get into a large debate there, so there's some people in here that are going to tell you the opposite of what I'm saying. But really we are using them as a relative merits of models. This model is better than that. We want to push them out, though, to get a wide enough range. So when you say, is there a model that we haven't considered? Our goal is to have the range be big enough so that the considered models are at least captured in there, but we won't have every single possibility.
So in particular, we've seen many earthquakes, not many, we've seen several interesting examples in close where we see some phases, sometimes called slap down phase, difference between the plus and minus on the acceleration records that is not typical in typical wave propagation. And it's probably some different kind of phenomenon that's going on that may not be included in current logic tree analysis.
So what we try to do is to see if there's a method that we're missing or something, something fundamental, we want to try to identify that and be sure we add it in and capture it in some way. And either we bring that method along directly or by looking at it from a couple of alternatives, so we could say that method might produce 3 times larger than what we would normally produce. So then we need to scale up one of our models at least to be high enough to capture that. So we do have we're not going to just use the models as they are published. We can push them up and down by other factors to try to broaden them out and capture those different approaches. But we need to have some model that's in some way to push it forward to get it to ground motion values so that we can evaluate those kinds of ratios. So if there's approaches, fundamentally that we're missing, beyond the empirical, we're looking at kinematic models and whether they have those detailed features, and then and they probably don't have what you're talking about, Tom. And then running some dynamic models, but we have to have enough a way to use them so that we have some confidence in the numbers that they are credible. So our goal really is to keep broadening out the alternatives and not miss something, and that's why we have you here to help us pick out, wait a minute, there's this whole class of models that you haven't taken on, and we need to then identify those and deal with them. Okay?
Vladimir Grazer, NRC. Norm, maybe it's a premature question, but as far as I recall, attenuation in Arizona is different from attenuation in California. Is there a plan to make some adjustments for anelastic attenuation?
Yes, and we have a session on that, so we'll get to that one. You said.
Yusuf Bozorgian, quick question. Why do you go to 2008 NGA West 1 as the base?
Why? Because that's what we had been running previously. It doesn't matter where those models are centered anyway, so we needed something. So it's somewhat arbitrary, but that's just a common set of models that are used in California or in the Western U.S. today. Do you have a better base case to use?
Adrian Rodriguez Marek. I know you're using finite fault simulations to constrain some, for example, hanging wall parameter. Is there any effort to look at whether the sigmas may also be different when you're looking at hanging wall? Because you are dealing with potentially some parameters that would quantify these motions that are not included in your simplified parameterization.
So far, no. And so I think part of what we want to get at is how do we want to use, for example, our simulations or the empirical data. So the empirical data are going to be too sparse to answer that question, right? We have barely enough to get at the median effect, let alone try to identify a sigma. On using the finite fault simulations, we've set out a set of ground rules saying they have to go through a validation process, and we're going to talk about that after lunch. That process right now has only been on the median. We haven't tried to get at the variability, but what I think we can do is look at the difference of the variability on the footwall side versus the hanging wall side. Even though I'm not sure we've got the variability calibrated for the absolute, you can see, is it increasing? And I think that's sort of addressing your question. So we should do that. Write that down, Jennifer, because that's easy to do, and that's probably a good way to start to use those simulations while we're not yet calibrated the standard deviation. That's going to be, I don't know if Christine is here, another year down the line in terms of what we're going to do on the validations of the models moving forward. So any other concepts in particular, moving forward trying to decide what will be the best use of numerical simulations, where should we be using them to help us here, addressing things. Because there's a lot of really interesting pieces that'll pop up, but we need to try to get what is going to help us that will most constrain the hazard or reduce the uncertainty in our hazard estimate, or broaden it if we have too small of an uncertainty. No other comments? Julian?
Julian Lozos at Pier. I have a couple of questions about the background seismicity and then normal events, just sort of trying to parse how you are setting that up. Are you saying that basically all of the potential normal faulting basin and range kind of events are included in that background? Or is there the potential for having something like the more rare event where you could have multiple normal faults, going off in sequence for like a cascading sort of jumping rupture kind of scenario? Or would the way you've parameterized the normal faults in there as background
So I think
allow that happen?
What's the maximum magnitude in your background zone, Melanie? Do you know? So it's
Okay,
big,
that
it's
would-
already large, but what we haven't been doing is in a more complicated, flower structure or multiple fault. The kind of problem that Jennifer and Katie were talking about when you've got two pieces and how do you deal with it. But we are making big events, they're just very rare. Okay, and anything else? You said you had two? Or no?
That was, I guess it was a multi-part question about multi-part rupture, so.
Okay. Adrian?
Adrian Rodriguez, will you have a single logic tree for strike slip and for normal, or do you consider a possibility that your weights would be different for normal faulting events than for strike slip events?
Yeah, so we may have a different weighting of the GMPEs for Palo Verde and for Diablo Canyon if necessary. Our goal is to try to keep those as similar as possible, but if you found that we needed to have a different weighting to really span the range of factors. Another alternative, though, is to just push out or add that epistemic uncertainty is by mechanism, and so we can increase it on the normal faulting. And I think that would be the first way that we're looking at it. But we could have different logic trees. We're not restricted to a common tree. We're trying to use as much of a common approach as we can for the two sites. Bob.
I'm Bob Budnitz from the Diablo Canyon Independent Safety Committee. Everybody in the room understands that what we're doing here is to try to understand what the seismic motion, what the situation is at the plant, so that we can understand whether the plant's current design is safe enough in terms of its resistance to earthquakes. And so my question is, in your work here, many of these uncertainties seem to be symmetrical, but some of them aren't. And I would urge, and you probably don't need this from me, but I'm doing it anyway, I would urge you to think hard about the high side uncertainties as being much more important than the low side, to be sure that you've encompassed everything and haven't missed something. Because it's there where, if we really understand them well, we can have a better handle on whether or not the design of that station really is encompassed under this umbrella or not.
Sure.
And I didn't see much discussion yet about whether these uncertainties are, to what extent they may be asymmetrical.
So you're right, the high side is, in terms of the mean hazard, the high side of the uncertainty is more important than the low side. The low side, we're driven by upper tails of distributions throughout the seismic hazard process.
Right.
So the distributions you saw, a lot of what Nick and Melanie were showing are just models as they exist. Okay, so there's no imposition of a symmetric distribution. Later on, in some of the trees that Katie put up, when we're dealing with additional epistemic uncertainty, when that, we're often estimating it as, there's some of those terms that are actually statistical looking in behavior, and you saw we probably put a plus or minus 1.6 times the standard error of the parameter. that's where we were assuming in symmetric distribution. You're right, we should broaden out our view on that and allow an asymmetric distribution if that's appropriate. That was one of our problems in Yucca Mountain, if you remember, of sometimes pushing a symmetric distribution on an asymmetric, something that is fundamentally asymmetric. So that's a point well taken, Bob, and we will be sure we don't anchor ourselves in a symmetric way just because it's simpler to work that way.
Well, but Norm, and you know better than I, there are two issues here. One is that some of the phenomena really aren't symmetrical about, and the other one is some of our understanding isn't. And boy, are they different.
Mm-hmm. Yeah.
And I don't have to tell you that.
All right. Okay, any other questions? One in the back.
I'm Sherry Lewis, San Luis Obispo Mothers for Peace. The question that I have, since I understood very little of what you were talking about, but something that did strike me is when you talk about the median of one rupture and the median of another, that is, I think that refers to the symmetry that Bob Budnitz was talking about. And I'm wondering, the trouble with the median is that we don't care so much about the median, we care about the extreme.
Sure. So that's fine. The median, so it's a convenient way for us to describe the problem, that there's a distribution and it has a median, and then it has some breadth to the whole thing. And we get both of them, but it's convenient for us to talk about it and parameterize the problem that way. So we don't just work with the median. In fact, much of what Bob was talking about, we care about the upper tails. That's really what drives it. But the mechanism we use to get there and the organizational structure is to say, what is the median, and then what is the variability? And Bob is also saying, and be sure you look at the asymmetry of that variability or uncertainty. All right, any other comments, Ken?
Am I allowed to ask a clarification?
Sure. He's going to get stereo.
Ken Campbell, PPRP. Yeah, I just wanted to ask a question. The current, for example, the NGA West 2 models that have hanging wall effects in them, some relied on the simulation model that Jennifer had developed, and it only went to 1 hertz. And so some of us had to decide how to push it beyond 1 hertz. Are you interested in periods above 1 second? And if you are you going to look at the hanging wall effects from the simulations and try to incorporate those somehow, because the GMPs don't very well?
So the answer for your clarification question, yes, we're interested in longer than 1 hertz. So we'll be running out to at least 5 seconds. And so as part of that, we'll be looking at what the simulations are showing us at those longer periods, both from the hanging wall and from the strike slip simulations as well. All right, we're at a stopping point. Okay, so lunch is just in the back. Is that it? Okay, so we're back at 1 o'clock. Is that correct, Corolla? 1 o'clock.
Well, when you start at 9, it gets to noon fast. When you start at 9:30.